Hello everyone, you're welcome to this channel once again. Today we have a peculiar question surrounding the damping ratio. How to calculate the damping ratio. Now let's read through the question given to us today. Assume that the rod shown in the figure below is rigid and massless. Also neglect the friction in the system if the mass M equals 80 kg and the stiffness K equals 8,000 Newton meters and the damping constant C equals 800 Newton seconds per meter, and the dimension are given as A equals 0.55 meter and L, which is the total length, equals 1 meter. Now calculate the damping ratio of the system. First of all, let's pull out the parameters. We are given the mass of the body to be 80 kg and the spring constant, which is 8,000 Newton meter given, and the C constant equals 8,000 Newton per second, and the length from the origin of the fixture to the damping and the spring contact equals 0.55, and the total length of the whole massless rod equals 1 meter. Now, by using the static and dynamic schematic point of reference, we can deduce that from the static, the balance equation of the static equals the Ka theta of the spring balancing with the damping Ca theta dot, which we can juxtapose with the dynamic equation of the rotation of the body, which is ml squared theta dot dot. Now, by comparing both equations together and juxtaposing it together, we find summation of the MO, which equals ml squared dot dot equals minus Ka squared theta minus Ca squared theta dot. So that gives us ml squared dot dot theta dot plus Ca squared theta dot plus Ka squared theta. Now, by linearizing it or comparing it to the standardized equation of mass system, which is ms dot dot plus cs dot plus ks, you can deduce that our m, that is the mass, equals ml squared and our c equals ca squared and our k equals ka squared. From the equation given, we can slot in all the values from the equation of the damping ratio, which is zeta. Zeta equals C over critical C. That gives us C over 2 square root of Km, which gives us Ca squared into 2 root of K squared into ml squared, which eventually gives us 0.28. So the damping ratio calculated from this particular problem equals 0.28. Thank you.